We're going to be doing this section 4.3 for the next 2 days. It's a long section, which is fine because it's meant to be due by Friday. And I'll give you a big picture. We'll go through what the whole thing's going to be, and then we'll go back to this. First thing we're going to do is look at graphs, and from the graphs, just the physical drawings, answer all these kinds of questions about when is it increasing, decreasing, when is it concave up, a happy face, or concave down, a sad face, and various coordinates. And then that's only for a couple of questions, and 3 more questions. We're going to look at the graph of the derivative function and answer very similar questions. So if I show you a graph of what the derivative of a function looks like, you can actually tell when is it increasing and decreasing and so on. And once those questions are over with, then we are actually going to use calculus, right? So we're going to use the first derivative and the values of that first derivative to answer questions about when a function is increasing, for what values of x is it decreasing, and the coordinates of local max and mins, if they have any. And a big chunk of questions that do that. About half as many, we're going to use the second derivative. And the second derivative doesn't tell you really about increasing and decreasing max and mins. What the second derivative function will help you do is find out about where things are concave up or concave down or points of inflection. And that's what those guys are. And then we'll tell you about a thing called the second derivative test, which essentially allows you with the first derivative to do these things. And then the last one, although there's only 3 questions, they're massively big. We are going to use calculus to sketch the graph of a function. Right, so here's a function, draw the whole thing, like you were doing Desmos, but doing Desmos by hand. And you've done a fair amount of that in 141. And we're just going to add a layer of calculus on top of it to give you a little bit more detail to what your graphs would look like. But they're extremely long because there's so many pieces, so many things you need if you want to draw a good graph, right? We're not talking about, well, it kind of looks like that, right? That's not the kind of graph we're talking about here. Well, let's start with the first one. I'll nip over to WebAssign. I think we did the first one, maybe. I'm sure we did the first one. Did we do the second graph? Do you remember if we did that one? Because I don't think we did. Right. Pretty sure we talked about the first one, or at least a version of it. Right. So what you've got here is a function that starts at x equals 0, and we'll assume it finishes. Well, do we assume it finishes at infinity? I wish they'd put little dots there. So I'm not sure about whether this continues or not. Let's assume it doesn't then. So when it says find intervals of x for which the function is increasing, from x equals 0 to 1, it's going uphill. So from 0 to 1.
You can type union in there and I'll put a union sign.
You mean the word union?
Yeah.
Oh, cool. Thank you. I'll do the next one then. Right. Where else is this function increasing? Tell me the value of x where it starts and where it finishes. When is this function, as you travel from left to right, going uphill? And zeros don't count. That's why we have curved brackets.
From 3 to 5?
Yes, I hear 3 to 5, which I think we're probably going to try and say at the same time as well. And well, let's try typing in the word union. And that's cool. And then it goes from 5 to 8. Okay. And that would be the increase. And now you might think, isn't it increasing from 3 all the way down? I'm saying 8. I think that's a 7, right? You might say, isn't it increasing from 3 all the way to 7? Well, technically, no. At that point, 5 isn't the function level horizontal. And horizontal does not count as an increasing, and it doesn't count as a decreasing, right? It's a transition point, right? Where one is turning into something else, or even the same thing. Can I? Oh, darn it. Oh, never mind. So you want to find out where it's decreasing. It goes from 1 to 3. So we're talking from x equals 1 to 3. You never include the endpoint. So I don't say square bracket 1 to 3. I just say 1 to 3. Find the intervals and when it's concave up. This thing has to go. Concave up. Is that a happy face shape or a sad face shape? Concave up.
Happy face.
Right. Not a technical term, but it works, right? Now, if I look at this shape, do you see it goes sad face, then it turns into happy face? Do you agree? There's a happy face bit here. Here is the sad bit here. Now, between this concave down turning into a concave up, there is a transition point. Would you agree roughly about the middle? So at x equals 2. So for that reason, it's going to be concave up from 2, which is here, and then it goes all the way up. Well, now we have a problem. You see this concave down bit? See that little sad face? No, it's not much, but it's like the left-hand part of sad. And you see the happy face coming up? I'm going to say 4. So it's concave up from 2 to 4. And it's also concave up from 5 to 7. Concave up doesn't need both sides. You can just be that side and still be concave up, right? You can still be that side and be concave up. It's nice when they're both there because you can see it a little bit better, but concave up only needs a piece of it. Do you see how from 5 to 7, you've got the right-hand piece of a smile? It's concave up. And so I said, I said 3 to 4, so that's my guess. And then we're going to go 5 to 7. And now I'm going to go up and I'm going to tell it to give me the answers to see whether there's an infinity involved or not. Go down, go up. I've lost the question. Here it is. Cool, I'm right. Did you notice it never put the union symbol in, it just put a comma? But really, you should put the union. That's the right term. Okay, so it was, those numbers do not have infinities. That's kind of what I was wanting to see out of that. If you're getting dizzy, I apologize. You have to go up and down in this thing to clear things. As we continue through the when is it concave down question, right, which is here, concave up was here, then you've got find the coordinates of inflection points. Now, a concave down makes a concave up. Right at the coordinate 2, 2. Do you see that point where my mouse pointer is? Hope you can see my mouse pointer. Do you see, isn't that where a happy face changes into a sad face and vice versa? So 2, 2 is one of those. Can you tell me the coordinates of the second inflection point?
4, 3.
Agreed. And where's the coordinates of the final third one?
5, 4.
5, 4. It's very visual, isn't it? If you know where to look, it's there, right? I think the hardest ones are when you have to do a kind of judgment call. And I tend to pick the middle you know, or a nice number that's close to the middle. And that is how you use a graph to answer all those types of questions. So I'm going to nip over here and show you an example of this type of question. How do you use the graph of a derivative to answer this type of question? And the reason I want to do one of my own is that way I can draw and point and so on a little bit more. So let's have a function that starts here. I'll make it obvious where it starts. And it goes up, and it goes down, and it goes up. And it does that. So here is my derivative function. I'm going to tell you that that's -2. That guy's at -1. That's obviously 0. This is 1. This is 2. I make that 4. I make that 5. And we'll finish at 8, right? I think I've got all the key places. There, that one, that one, that one, that one, that one. No. Chloe, come out of there. No pulling wires today. Okay, so you have to remember that this is not the original graph. This is what the derivative graph would look like, right? So if you differentiated and plotted that. So if you want to know, for instance, when a function is increasing, and I should say, when is f of x increasing to make it more obvious? Here is the property. The derivative will be greater than 0, right? The derivative will be positive when it's increasing. Can you imagine if a function's going uphill, won't its derivative be a positive slope? Right. What happens when a function's curving downhill? Won't the derivative be a negative slope? That's why it works. So you're increasing when this is happening. The function is decreasing when that's happening. So, oops, I better put a point at the end here. There, it's -3. This function is increasing there. I'll put it, my answer's here then. From -3 to 2, right? Because from here to here isn't the derivative below the x-axis. And if you're below the x-axis, doesn't that mean you're a negative number, right? Your value is negative. It's also going to be decreasing between here and here. So that will be from 0 to 2. Now you might look at that and say, isn't it decreasing from 45? But the reason you're probably thinking that is that you're forgetting that this is a derivative function. Yeah, you're right, the derivative is decreasing from here to here, but that's not what we're after, right? We're after is the original function decreasing. Are we cool with that? Now, if you want to know when it's increasing when the derivative is positive. So it's increasing from -2 to 0. And it's increasing everywhere else. So that's what, from 2 to 7, 2 to 8. So are you comfortable that if someone shows you the graph of a derivative function, that the values where it's above the line are when it's increasing, and the values when it's below the line, the x-axis line, is when it's decreasing? So far, so good. Now, you can actually find the, why is that doing that? You can actually find the x coordinate of a local max and the x coordinate of any local minimums. This shape has 3 combined local max and mins. Can anyone tell, just by looking at this graph, where they are? You don't need to tell me what they are, just where they are.
-2, 0, and 2.
And the reason that they're there is it not the place where the derivative is 0? And if you think of a derivative as 0, isn't that typically happens at the top of a hill, a local max, or at the bottom of a valley, a local min? It doesn't always happen there, but let's read it. It will always happen there, but sometimes you get a 0 derivative where it's not a local max and min. So here goes. This is negative, this is positive, right? So what you have is a sloping down, a 0, and a sloping up. Do you see at that point there, negative derivative, the graph is sloping down, 0 derivative, positive derivative. That makes this guy here, what's that? Put it in the wrong place. At x equals -2, that's a local minimum. Right, what about it 0? Well, it's positive, 0, and negative. So it's positive, 0, and negative. That guy is a local max. What is happening at x equals 2? A local max or a local min?
A minimum.
Check it out. Here, it's a negative number, slows down. Here it's 0, and here it's up. Now, if you think about it, if I put this one in first, if you think about it, there's only really 2 kind of patterns that happen, right? A local maximum, which is this one, will happen when the shape looks like this. And the other guys, they look like that. Do you see the changeover, the way they point? So if you see something pointing uphill like that, it's strange, but pointing uphill like that is actually what a local minimum looks like. And see pointing downhill here, that's actually what a local max looks like. So if you do enough of them, you can just say, yep, min, max, min. Now, I said it is possible for you to have one of these zeros that is not a local max or min. So let me show you that on a different picture. Make that 9. Can you imagine a function that does this? It touches the x-axis, right, and then it goes back up. In this case, won't the derivative be positive on both sides? So what would that look like? Well, if the derivative is positive, the original function goes up, then it's 0, and then it goes up. You get one of those kind of hills that levels off for a second. That is not a max or a min, right? Now, still not finished, because we can get one more piece of information out of this shape. We can find the x coordinate of points of inflection. Where do you think the 3 points of inflection, because there's 3 of them, are? This is the graph of the derivative. Where are the 3 points of inflection?
Zero, 3, and maybe 4.5.
No, but I know why you chose them. That's exactly where they would be if this was a sketch of f of x. But this is a sketch of not the original function f of x, because your answer would be correct if it was that. This is the sketch of the derivative function. So the points of inflection are actually somewhere else. Any ideas? Last chance? They're actually at these places here. That looks a bit strange. Tops of hills and bottoms of valleys of derivatives are where the points of inflection live. So there's a point of inflection at -1. There's a point of inflection at x equals 1. And there's a point of inflection at 4. So those guys are the points of inflection. Now you might think, why is that the place where they are? Why can't they be like somewhere else? For instance, take that number 0. X equals 0, isn't that where the local, in this case, where the local min lives, right? It's not one of our guys. At this point here, the function is positive and getting steeper, right? So if you imagine what that would look like, oh, this picture's getting messy, but the original function, right, from here to here, right, it's positive and getting bigger. Positive means you're going uphill and getting steeper, right? And then what's happening here is that it's getting less steep and less steep. So it's going to go something like that. So can you see there's a transition between a happy and a sad face? I don't know if that's very convincing, but the tops of hills and the bottoms of valleys of the derivatives, and now that I've said that, I missed one, isn't there? There's another one at 5. But that is a lot of information that you can get out of just the sketch of a derivative function. So we're now going to go and look at one of the examples of that. On our homework. Okay, I can make that bigger because it's the graph that's important. Okay. Where shall we start? Tell me an interval where the function is increasing.
Zero to 1.
Okay, where else is it increasing?
3 to 5.
Yep. Where's it decreasing?
1 to 3.
And where else is it decreasing?
5 to 6.
We all agree you can, above the graph is increasing, right? Above the x-axis is increasing. Anything that's below is when it's decreasing. We have 3 places on this graph where a local max and or local minimum is happening, right? What are the x coordinates of any place where a local max or min is happening?
1, 3, and 5.
Great. 1, 3, and 5. Now, how about, is there a local max at x equals 1, or is it a local min at x equals 1? So on this
Max.
side, it's okay. And this side, it's positive. That means the graph's going up, 0. So that, right. See when it points, what, from left to right? That's a max. So at x equals 5, right? Left to right, it's a max. At x equals 3, isn't it the other way around? So that would be a min. Right, last question. What are the x coordinates of the points of inflection in this graph?
2 and 4.
2 and 4. Are you beginning to get an idea of how you can use the derivative to get all those kind of things that you might want to do if you were sketching? It's pretty much the same. Okay, this one's got lots of bumps in it. For this one, tell me the interval where the function, tell me an interval where the function's increasing.
0 to 4.
And another place.
6 to 8.
And then decreasing 46. I'm always a little bit worried when they have a graph that finishes there and they don't have a number. So it could be decreasing from 8 to 9 or 8 to infinity. You're going to have to figure it out when you try your answer. If 8 to 9 doesn't work, do 8 to infinity and it will, right? They really should have little arrows on those, shouldn't they? To kind of indicate it. I think it's pretty obvious there that the graph stops because you see there's nothing left. But if you want it to stop, just put a dot at the end, just make it clear. If you want it to continue, put an arrow at the end, right? Make it clear. Okay, last question for this one. Wow. How many points of inflection does this graph have?
5?
5. That's a lot, isn't it? Give me the x coordinate of any of them.
3.
You agree there's a top of the hill there?
Uh-huh, 1 and 2.
There's one at 1, there's one at 2, there's one at 3, there's one at 5, and then finally there's one at 7. So there's like, this graph must be like a sine function. Do you know a sine function that's going happy, sad, happy, sad, happy, sad, right? This function's got a lot of wibble in it, a lot of wiggles, or whatever. That's not an official name. And we are finished with the graphs. So if someone gives you the graph of the original function, or they give you a graph of its derivative function, you can find lots and lots of things to do with increasing and decreasing and points of inflection. So now we're going to have to do the calculus of, we're only interested right now in finding local max and mins and when a function is increasing and decreasing. So this is, what is this one? This is number 6. And so the function that I'm dealing with is 2x cubed, take out 12x squared, plus 18x take away 2. Now, since we are interested in this information, intervals of x where the function is increasing, decreasing, and we want to know coordinates of any local max and mins that there are. And there's, how many of those there are? There are 7 questions where we're pretty much going to be doing the same process. So the first thing you do in this type of question is you find the first derivative. So in this case, it's going to be 6x squared, take away 24x plus 18. Once you've done that, you find what are called the critical numbers. And that is going to be, for almost every question, when is the derivative 0? And for some questions, it's also going to be, when is the derivative undefined? But in this case, the derivative is not going to ever have a problem with that, but for completeness sake, I'll put it in. This undefined situation is only going to become important if the function has a square root in it, you know, like it's x to the half, or if the function has a fraction to it, right? It's 5 over x squared minus 4, that kind of thing. Then you might be interested in that. But most of the time, you're going to be interested when the derivative is 0, and that's what we call the critical numbers. So to do those, right, Cn, define the critical numbers, we have to solve when is the derivative equal to 0. In this case, we're going to solve that guy. I don't like factoring quadratics with big numbers next to the x squared. In fact, I don't like it. If there's any number next to the x squared, it just makes it so much harder to do. Can you see any common factor that I could pull out before I start any more factoring?
You pull the 6.
Always look for that if you can, if there's one there at least. Now at this point, factoring never goes away in calculus or anything in math. Tell me the two factors that work.
-3 and -1.
Correct. How did you do that? Just curious.
Well, it had to be -4 and 3 was smaller, so it had to be something times 3.
Mm-hmm. And they both had to be negative as well, right?
Yeah.
Yeah. Well, that gives us our critical numbers. There is a local max or local min, or just one of those what are called horizontal points of inflection, right? That's the ones that don't really do either. And they can only happen at these two locations. So now we go on to finding out all the answers that we want, and we get them in one go by this step. We're going to create a thing called a table of signs, which is kind of strange because it's not really a table unless you do it the way the book does it. It's really a line, so it's a line of signs. So you draw a number line that represents values of x. We know that the answers to the critical number is 1 to 3, so I'm going to start at 0. I'm going to go 1, 2, 3, 4, 5, I guess 6 if I wanted to. And there's my x. X equals 1, the derivative is 0. And at x equals 3, the derivative is 0. You then choose what are called test points. I want you to think of these zeros as breaking this number line into 3 distinct pieces. You see, you've got, I'll give them names. I'll put even little invisible dotted lines that don't really exist. There's A. Region B is in here. And then lastly, region C is over here. Right, that's the 3 regions. Now you pick test points. What I mean by that is pick an X coordinate, any X coordinate you like in each of these regions. So in region A, I'm going to pick x equals 0 because I like 0. In region B, I'm going to pick a nice number like 2. Could I pick 2.01537? Of course I could. But wouldn't that be a really stupid one to pick, because it means my calculations are going to be hard, right? And I don't want hard calculations. I want easy calculations. So anybody want to give me a volunteer for C? Give me a test point in region C.
5.
5.
5 is a good number. Won't 4 or 6 also work? Won't 3.1 be a bad idea? Now, for each of those guys, you find the value of its derivative. And I'll show you what I think is the quickest way to do it, but you might find other ways that you prefer. I go into my calculator and I type in my derivative function. I don't even worry about it not being factored. I'm just going to type in 6x squared, take away 24x plus 18. And then I'm going to do second table setup. And I'm going to make sure I start at 0 and make sure that says ask. And that's it. I'll now go second table. I'll rub out all data and I'll put in 0 and the answer is 18. I'll put in 2 and the answer is -6. And I'll put in 5 and the answer is 48. Would you agree that's relatively easy to do, and you don't need to worry about your answer being wrong, won't it? Because the calculator's doing pretty much the heavy lifting. Now, those derivatives, right? Those derivatives at these key points, these test points, I don't actually care that it's 18. All I care about is that it's positive. And that's negative. And this is positive. So that's the only things that matter. So you go up here and you say, okay, you're positive at that number, and you're negative at that number, and you're positive at that number. And then we make this following assumption, that if you're positive here, you're going to be positive in all these places. Everybody in C is going to be positive. And in region B, you are negative. Everybody in B is going to be negative derivative. And in A, you're positive, and everybody is going to be positive. And you might say, well, how can you make such an assumption based on the fact you just found one answer? And the argument goes something like this. If you go from a positive to a negative thing, and it's continuous, right? It's smooth. The only way to go from positive to negative, would you agree, is that you have to be 0 somewhere, right? If you start off positive and then you become negative, you have to be 0 somewhere. Well, if this guy is negative, everybody in here has to be negative, because if there was a negative and then next door there was a positive, wouldn't there have to be a 0 somewhere in region B? And we know that there aren't any more zeros, right? We found the only ones that live, and that's the argument. Right? Now, this guy up here is going to tell us everything. So step 4, get your answers. So let's find when the function is increasing. Right? By that, what values of x is a function increasing? Can you remember what the derivative is equal to when something's increasing?
It's positive.
And so won't that be everybody here? Right? Region A. Now region A goes forever. So negative infinity up to x equals 1. And from, what's that, x equals 3 forever. Does that make sense? It's increasing when the derivative is positive, right? And it's going to be decreasing when the derivative is negative, which in this case is between what, 1 and 3. So as long as you pick a value of x between 1 and 3, this function will be decreasing. Now, the other two things that you're going to get from this table of signs is the x coordinate and then later on the y coordinate, but the x coordinate of local max and local mins. So let's see if we can figure out what they are. I know where they are. If they're going to be anywhere, they're going to be at 1 and 3, right? That's the only place they're going to have, right? When the derivative is 0, that's where local max and min. Let's look at x equals 0. Sorry, x equals 1. Now at x equals 1, values to the left of 1, right, like x is 0.5 and so on, are positive. And positive means that the curve is going up the way, right? And 0 means it's flat, and then it's negative. Can you see that that combination is a local max, right? Positive, 0, negative. So at x equals 1, there's a local max. Okay. The other place is at 3, right? Now, in this case, the derivative is negative, means the original curve is going to be pointing down the way. Then it's 0, and then it's positive. Can you see then that at x equals 3, we have a local min? And if you want to know the coordinates, it's 1 comma something, and then it's 3 comma something. Now, to get the coordinates, you have to go back to the original function. So the value of the function at 1 is 2, 20, 20 take away 14 is 6. And if you want to know the value of the function at 3, it's, oh my God in Himmel. It's too hard to do in my head. So let's find out what it is. It's 2 times 3 cubed. Subtract 12 times 3 squared. Add 18 times 3, and then take away 2. And the answer I get after all that hard work is that it was -2. So there is our original function. It's increasing in these, for these values of x in this range. It's decreasing for values of x in this range. And there's a local max at 1, 6. And there's a local min at 3, -2. So far, so good. Now that's all you're asked to do. I'm going to show you a kind of pseudo version of what I can get from just using this information. At 1, 6, so can you imagine 1, 1, 2, 3, 4, 5, 6. At 1, 6, there's a local max. At 3, -2, there's a local min. Can you see very, very roughly right now? Don't I know what the original function looks like? And if I had time, which I don't, I would go to Desmos right now and show you that that's a pretty good representation of what's going on. Now, what I haven't made any attempt at really doing is finding, you know, those coordinates, because couldn't they be different from where I'm drawing? Because I'm basically just freehanding a hill and a valley, right? So this might be a little bit further over, right? This might be a little bit further over. This might be a little bit lower or a little bit higher, but isn't the basic shape correct? That's all you're getting right now, the basic shape. And I think we learned some cool stuff today. So last name, and bye-bye. I'll hang a bit for any questions.
Thank you.
You're welcome.
Thank you.
Any questions? Jamie or Dylan? If not, I'm going to close off. Jamie? Okay.